Gnanam Paramam Dheyam. Knowledge is supreme.
We have seen that finite subgroups of the unit group of a field are cyclic, and we want to consider one important example where we will use this fact to describe what is called roots of unity. So let me write this as an example. Roots of unity. So let K be any field and N be a positive natural number. Actually, I want to call not K but L. L any field and N be any positive natural number. Then look at the unit group of L, and we have a natural map here, namely the power map N. X goes to x power n. This is the power map. This map obviously is a group homomorphism. So therefore it makes sense to talk about kernel. Let me call it chi n. So kernel of chi n, this is a subgroup of L cross, and this subgroup is precisely all those elements x in L cross such that x power n is identity. So this is also, these are precisely the nth roots of 1. So this is denoted by mu n L. It depends on n and it depends on the field L. So this is a subgroup of L cross, and in fact it is a finite subgroup. In fact, the cardinality of mu n L is at most n, because mu n L is precisely, in our earlier notation, if you remember, mu n L is same as V L of the polynomial x power n minus 1. They are precisely the zeros of this polynomial. So it's, and this cardinality is less equal to n. So cardinality of mu n L is less equal to n. So therefore it is a finite subgroup of L cross. So we know it is cyclic. So mu n L is a cyclic subgroup of L cross. So zeta be a generator, let zeta be a generator of mu n L. Then first of all note that zeta power n is 1, that is by definition of mu n L, and therefore order of zeta will divide n, and this is order of zeta is same as cardinality of mu n L. So when the order is n, if order of zeta is exactly n, then zeta is called a primitive root of unity, primitive nth root of unity in L. Note that the primitive root is defined only when the order is precisely n. So it is in this case, when one talks about primitive nth root, that means mu n L has order n and zeta is the generator of mu n L. So third, now note, if characteristic is P, what happens? If characteristic of the field is P, which is positive, in the case, you write this given n as, take out as much as power of P can come out, P power alpha times n prime, where P doesn't divide n prime. Then mu n L and mu n prime L, they are same, because when somebody belongs here, x belongs here, means what? That means x power n is equal to 1 or minus 1 is 0, but this is equivalent to saying x power p power alpha n prime minus 1 is 0. This is equivalent to saying x power n prime minus 1 power p power alpha is 0, and this 0 is all are in L. But L is a field, so this is equivalent to saying x power n prime minus 1 is 0 in L. So that is equivalent to saying x is in mu n prime L. So the groups are not changing if you throw away if you cancel the power of the characteristic from n. So therefore, when we may assume therefore to study, so I will note it down, very important reduction. So to study the subgroup mu n L, we may assume that P, a characteristic of L, and N are co-prime. The GCD of this is 1. Already characteristic 0 we don't have to assume anything, characteristic P we have to assume P doesn't divide 1. But this can be neatly written as, this is equivalent to saying N is not equal to 0 in L. When you say N, that means N times 1. This is not 0 in L. That is where if the characteristic is positive. If the characteristic positive, if the characteristic 0, this is always true. So that is a very important reduction to study the roots of unity. And we will come back to it when we construct field extensions whose the Galois group is precisely this group. Okay, all right. So now I want to come back to a proof the structure of the finite fields, or L be a finite field. Then first of all last time also we noted that the cardinality of L must be power of a prime number, p power m, where p is prime and m is a non-zero natural number. This is because we know that the characteristic of finite field must be a positive, characteristic L must be P positive, and then L will contain a prime field Z mod P, and because L is finite, a dimension of L as a Z mod P vector space, its positive M finite dimensional vector space. So therefore this L will be isomorphic as a vector space to Z mod P power M. In particular, cardinality of L must be cardinality of Z mod P power M, which is Z mod P cardinality power M, so which is P power M. So we proved that if you have a finite field, the cardinality is nothing but power of a prime number P. Conversely, I want to prove that if I have any finite field, conversely given P, given a prime number P, and a positive natural number M, we want to construct a finite field L with cardinality P power M. For M equal to 1, it is obvious the field you can take is Q power Z mod P. Okay, so proof. So we have given P, so that means we have given Z mod P. And then you look at, we therefore can look at the polynomial x power P power M minus x. This is a polynomial, think of this as a polynomial over Z mod Px. Alright, now I want to use Kronecker theorem. Kronecker theorem says that given any polynomial over any field, I can find a bigger field so that all the zeros of that field of that polynomial lies in that field. So by Kronecker theorem there exists a field extension, finite field extension, L prime of Z mod P such that x power P M minus x, this polynomial splits into linear factors in L prime x. And this is a finite field extension of this. So in particular, L prime is also finite. Alright. So L prime is also finite field. And anyway, I want to consider all the zeros of these polynomials. So zeros of this polynomial V P power M minus x in L prime. So this set I want to call it L. So they are the zeros of this polynomial and they are precisely, okay, we'll worry about how many are there, but right now we check that this actually form a subfield. So for that I have to check that, so we will check that L is a subfield. So for this I have to check it is closed under addition and also multiplication and the inverses of course. So that means if x is a 0 of this, y is a 0 of this, then x plus y is also 0 of this. That's what we have to check. But for that is very easy. X plus y power P power M. This is because the characteristic is P. X power P power M plus y power P power M. But x power P power M is x and y power P power M is y. So therefore this Similarly this, and also x inverse power p power m equal to x inverse. That is, you don't have to check this because okay, for this is when x is not 0. So it is a subfield. Alright, now if I want to claim that the cardinality of L is precisely p power m, but to check that, I have to check that this polynomial, so this is if and only if the polynomial x power p power m minus x has precisely pm distinct zeros. That means I have to check that this polynomial, all the zeros are simple. So to check this, so it is enough to note that the polynomial x power p power m minus x has simple zeros. That means no repeated zeros. And how does one check that? One has to differentiate and check whether that is a zero of this. So let x be a zero of this polynomial. Let us call this polynomial as f. And I want to check now, to check that if I take f prime and evaluate at the small x, this is not 0. But what is f prime? F prime, we have to differentiate this polynomial with respect to x, but p is a characteristic. So this is p power m times x power p power m minus 1 minus 1. But this is 0, p is 0, therefore this is 0, so this is minus 1. So therefore f prime x is minus 1. It's a constant. So and minus 1 cannot be 0. Minus 1 is not 0 in L. Therefore, we have checked that this polynomial has only simple zeros and it has precisely therefore p power m 0. So that checks that the zero set of this polynomial in arbitrary field extension where this polynomial splits has precisely m p power m elements, and that is the required field. Now we have to prove the uniqueness. So uniqueness. That means we want to prove that if I have two fields of the cardinality p power m, then they are isomorphic. So suppose, I will write a statement first. The field L of cardinality p power m is uniquely determined. Up to isomorphism. Okay, that means what? That means if I have two fields L and L prime, fields with the same cardinality p power m, then I want to find an isomorphism here. Alright. So let us look at L cross. Now L is a finite field. So this is a finite subgroup of L cross. So this group is cyclic. We have proved it. So let X in L cross be a generator. Okay, now this L contains Z mod P because characteristic is P. Characteristic has to be P. We have noted that if the power is the cardinality is power of P, then P has to be the characteristic. So it will contain the field Z mod P, and because this L is a finite field, this extension is a finite extension. In fact, finite of degree m, and in particular, therefore, algebraic. L is algebraic over Z mod P. So in particular, this element X, which is a generator of L cross, is algebraic over Z mod P. So let mu X be a mu X belonging to Z mod P, X be the minimal monic polynomial of X over Z mod P. X over Z mod P. Alright, so what is L? So now therefore what do we know? The property of the minimal polynomial, that is when I take Z mod Px mod ideal generated by mu x, this is isomorphic to Z mod P adjoin X. This is precisely, remember the evaluation map, the polynomials evaluating at the small x. The kernel is precisely generated by the minimal monic polynomial, and the image is precisely the subfield generated by X. So this is a field, and this is an isomorphism of fields. Alright, but this is what? Because X is a generator, this is precisely L. X is a generator of L cross. L cross means every element of L cross are the powers of X, and therefore in particular they are polynomials in X. So this field is precisely L. Alright. Now we know that this polynomial mu x is 1, and look at the other polynomial x power pm minus x. This is a polynomial where x also satisfies because x is an element in L. So therefore mu x, this polynomial is in the kernel, therefore mu x has to divide, mu x divides this polynomial in Z mod Px. In Z mod Px, because this is a polynomial where x satisfies, and this is another polynomial where x, this is minimal, so therefore this has to divide this here. But when this polynomial has all roots in L, therefore when you throw away x, take a common factor x, p power m minus 1 minus 1, this polynomial is precisely the product of x minus a, where a varies in L cross. Because when I throw away x, you get this polynomial has distinct roots. When I throw away one x, you get a polynomial of degree pm minus 1, and L cross also has m elements. So all the linear factors will occur there, because so this polynomial splits like this in Lx. This splitting is in Lx. In Lx, this. Now let us take the L prime was another field. L prime another field with p power m elements, and we have noted that this polynomial x power p power m minus 1, this splits into linear factors in Lx, L prime x also. So therefore, and mu was the factor of this. Therefore, we know there exists. So in particular, there exists x prime in L such that mu x of x prime is 0, because mu was a factor of this, mu was a factor of x power p power m minus x. Therefore, there will be 1 and x is not 0, so x prime will be a 0 of this mu. And then we have this map. Look at the map, z mod p x to L prime. The map is the evaluation map epsilon x prime. So x, capital X go to x prime. Then obviously this mu goes to 0. So therefore we will get, so this will induce this epsilon x induces z mod p x modulo ideal generated by mu x to L prime, because mu is in the kernel of this max, since mu x belong to kernel of epsilon x prime. But now this is a field. This we know this is precisely z mod px small x, but this is precisely L. So this is a field and this goes inside this L prime. So this map, this epsilon x prime, this map bar, this map is injective, because this is a field. So from a field it cannot have kernel. Field has no ideal other than 0 and itself. So this map is injective and also surjective, because surjectivity will follow from the fact that both L and L prime have the same cardinality. So pigeonhole principle will tell you in the injective map same cardinality set has to have bijectivity. So since cardinality of L equal to cardinality of L prime, so therefore this is actually an isomorphism, because it's bijective map, so it's isomorphism. So that proves our claim that L and L prime are isomorphic. So remember that we have proved two very important observations today, namely one was every finite subgroup of group of units of a field is cyclic, and we have used that fact to check that any two finite fields of the same cardinality are isomorphic, and cardinality of a finite field can only be power of a prime, and any two such fields are isomorphic. So we have also constructed them explicitly, how to construct, and the construction is by using the polynomial x power p power m minus x, and We will continue in the next lecture. Some more consequences I want to deduce from these observations.